Welcome back. This time we're going to talk about descriptive statistics and inferential statistics. We're going to use an example to demonstrate the difference between descriptive and inferential statistics. And we're going to learn how to calculate the mean, the median, the mode, variance, standard deviation, and the z-score. These are the key descriptive statistics, especially in experimental research. We're going to review a little bit on the differences between a theory and a hypothesis. And then we're going to talk about the logic of hypothesis testing. We're going to talk about the significance level, the p-value, the research hypothesis, and the null hypothesis. Let's look at an example. I have a theory. I have a new drug. I have developed a new medication for people affected by the COVID-19 disease. According to my theory, this new medication, which I call reserach, of course this is made up. I don't have any new medication for the coronavirus disease. But suppose my theory is this new drug, reserach, can speed up the recovery of COVID-19 disease patients. How do I test this theory? How do I provide some support of this theory? I cannot just sell the drugs to COVID-19 patients. The authorities, the FDA, will ask me to provide evidence. They will ask me to show that the drug actually works. It actually does help people recover faster from the COVID-19 disease. How do I prove my theory? Can I prove my theory at all? No. We can never prove a theory because your theory is abstract and broad. In terms of this theory, reserach can speed up the recovery of COVID-19 disease patients. I am referring to patients all over the world, patients in all countries, and more importantly, I'm referring to patients not only today, but the patients of the future. Even next year or even in 5 years, if some people get affected by the COVID-19 virus, if they get the disease, this medication will help them recover faster. I cannot observe all patients all over the world. I cannot observe patients in the future. So a theory is not open to observation. It's abstract, it's broad. The best we can do is to support hypotheses derived from your theory. If your theory is right, what should you observe? What should you find in your observation? You can make concrete predictions based on your theory. A good theory gives you concrete observations, gives you concrete predictions. This is called a hypothesis. A prediction based on your theory that can be observed is called a hypothesis. In this case, I can develop a very concrete hypothesis from my theory. My hypothesis is that if I randomly sample 10 people with COVID-19 disease and make this my sample, then if I divide my sample into 2 groups randomly, if I give one group the real medication, which is called reserach, and then give the other group the placebo. The placebo is a medication that is a fake medication. Basically, it's a pill that looks just like the real medicine, but it doesn't contain the chemical ingredients of the medication. And my prediction is that the group taking the real medication will recover faster than the group taking the placebo. This is a concrete and specific prediction of what we can observe, what we should observe if my theory is true, is correct. You can actually recruit 10 people and you can actually divide them into 2 groups. You can actually give them different medication, the real versus the placebo. And then you can actually observe and record how long does it take each patient to recover. And you can do your data analysis and observe on average, does the group taking the real medication get well faster than the group taking the placebo? If your hypothesis gets supported, your theory gets support. We cannot prove a theory, but we can provide evidence for a theory by finding support for a hypothesis derived from a theory. A hypothesis tells you how to design your research. Once you have developed a good hypothesis, which is specific and concrete, you know how to design your research. In order to test this particular hypothesis, I need to do an experiment. I need to conduct an experimental research. And in this particular case, my independent variable is the type of medicine, the type of medication given to the patients, given to the sample. And for this independent variable, I have 2 levels. One level is the real medication, reserach. The second level is a placebo. So I create 2 groups. One group takes the real medication. The second group takes the placebo. The dependent variable is how fast each person recovers, how fast each person gets well, how many days it takes people to get well. And I need to be very specific about how I measure this variable. Exactly how you measure a variable is called operational definition. You need to provide operational definition for the variable of recovery time. What do you mean? What do you mean by recover? Do you mean that there's no fever? Do you mean that the virus is gone? The virus test becomes negative? Do you mean that there's no complaint of a pain in the lung? Do you mean there's no coughing? Do you mean all of this? Disappearance of all COVID-19 symptoms? You need to be very specific in specifying how you measure recovery time. This is called the operational definition. Operational definition of the variables are very important because you want other people to repeat your experiment. If other researchers can repeat your experiment and consistently find the same results as you do, then you have a strong support for your hypothesis. You have a strong support for your theory. Repetition or replication is very important for supporting hypotheses and theories. In order to help other people, other researchers replicate your study, your experiment, you have to specify how you measured your variables. This is operational definition. In this group, in this experiment, we have two groups, an experimental group and a control group. The experimental group is a group taking the real medication. Why do we call the group that take the real medication the experimental group? Why don't we call the placebo group the experimental group? This is because the medication, reserach, the active ingredients of this medication is what we are interested in. We are experimenting with a real medication. The control group or the placebo group, the group taking the placebo, is just for comparison. It's a comparison group. We want the placebo group to provide a benchmark for what kind of improvements we should observe. Well, if our hypothesis is supported, we should observe that the real drug group, the group taking the real drugs, real medication, should improve even faster than the control group, even faster than the group taking the placebo. The real medication should work even better than the placebo. It's not good enough to work as well as a placebo. This is basic structure of the experiment. Let's look at the data. Suppose you finish the experiment, you completed the experiment, you randomly selected 10 people from, let's see, I have actually more descriptions here. In your research methodology, you draw a random sample of 10 COVID-19 patients from the Royal Climbing Hospital. This is the first part. So first step, you get your sample. The sample consists of 10 patients. And the population that this sample represents is the Royal Climbing Hospital patients. All patients who are receiving treatment at this particular hospital for COVID-19 disease. Your sample cannot represent all Canadian patients because you didn't sample from the Canadian patient population. You're sampling from a population who received treatment at a particular hospital. Pay attention to the correspondence between your sample and your population. And you randomly assign 5 people to take the medication, the real drug, and the other 5 people to take the placebo. And you use a double-blind design. What is a double-blind design? Double-blind means that each patient doesn't know whether he's taking the real medication or the placebo. This procedure prevents bias, prevents expectation effect. Suppose if a patient knows I'm taking the real medication, this is the real stuff, that might influence his or her feeling about his or her symptoms. He might feel better. And if a patient knows he's taking the placebo, well, I'm taking just a fake pill, this is not real medication, and then this knowledge might influence his or her feeling about his or her symptoms. You don't want this kind of influence on the patients. So the subjects have no idea what kind of medication he or she is taking. And then the researcher who is collecting the data, who is measuring temperatures, who is asking each patient about how well or how ill he or she is, also doesn't know what kind of medication each patient is taking. The researcher actually collecting the data is also kept in the dark. You don't want the researcher to be influenced by the knowledge of what kind of medication each person is taking. If a researcher say, Suppose if a research assistant is responsible for giving out all the medication and for making all the observations, collecting all the recovery data, well, this knowledge might influence his or her perception of how well each patient is. You don't want this kind of expectation on the researcher either. So the researcher responsible for collecting the data and running the research is kept in the dark. Of course, somebody must keep track of what kind of medication each patient actually takes. There are researchers who are in the know, but the researcher who is doing the hands-on work, collecting the data, must be kept in the dark. This is what we call double-blind design or double-blind procedure. The patient is blind to the treatment conditions, and the researcher collecting the data is also blind to the treatment conditions each patient receives. We have very good, very solid, very rigorous design in this clinical trial, and then we get the data. These are the data from the experimental group, the real drug group. They receive the real medication, drugs. And we have given numbers to each subject, each patient. Patient number 1, 2, 3, 4, 5. We have 5 of them. They have been randomly assigned to take the real medication. And we measure how many days it takes them to recover. The first person, it takes 4 days. It takes 4 days to recover, 6 days, 7 days, 8 days, 3 days. And then we have another group, the control group. This group takes a placebo, 1, 2, 3, 4, 5 patients. And then each patient is recorded on how many days it takes him or her to recover. The first patient in the control group takes 5 days, 8 days, or 3 people took 8 days to get well. And one person is really fast, only 3 days. He's well, he's up and running, back to normal. Well, just by eyeballing the two groups, data of the two groups, you get a feeling, okay, it seems that the first group, the experimental group, on average, it seems to be faster in recovering from the disease. You see a lot of 4s, 3s, 6, 7, 8s. But in the second group, the control group, it might take longer. More people take 8 days to recover, but you are not sure. Just by looking at the individual data, too much differences. People differ from each other. Even in the control group, even the people who are taking the placebo, there are some who are really fast in recovering. Say you have 3 days recovery, 5 days recovery. And even in the group that takes the real drug, there are fast people, there are slow people to recover. Even in the medication group, you have somebody takes 8 days to recover. So the individual data on the individuals give you a feeling, might give you a sense, but the individual differences, individual variability gets in the way. Doesn't give you a clear idea of what's the difference, what's the average difference between the two groups. So we need some descriptive statistics. We need to calculate the means. Let's calculate the mean. The mean is a very common way to understand the average characteristic of a group. Let's calculate the mean. You know, in order to calculate the mean, the first step is to calculate the sum. The sum, you add all the numbers up. So in this case, the sum of the group is you have a 4, you have a 6, 7, 8, and then you have a 3. Add them all up, so that's 10, seems to be 28. 28 is a sum. And then actually the mean is the sum divided by how many people in your group. So you have a 28 over, let's see, 5 people. You have 5 people in the group. Let's see what's, I'm going to get a calculator. Okay, I got a calculator here. 28 over 5. Okay, that's 5.6. On average, these 5 people took 5.6 days to recover, to get well. And then, well, I'm eager to see the other group. How many days on average that group took to recover? We will get the sum of this group. So the first person in this group took 5 days, and then 8 days. 3 people took 8 days to recover. These guys or these girls will blow up the number of the group average, and then you have one fast recoverer, 3 days. Wow, let's see what is a sum. Seems to be, let's see, 32. 32 is the sum of this group. On average, let's calculate the average. The mean is, again, the sum divided by number of people in the sample is 32 over 5. 6.4 days for the second group, for the placebo group. The mean looks really good. So the group that take the medication took them 5.6 days to get well, but the group that takes the placebo took 6.4 days to get well. Seems this data supports my hypothesis. Looks really promising. And here is the trick. Are you sure that the data supports your hypothesis? I'm not so sure. Well, science is all about debate. Scientific research is like a debate between two sides. I invented the drug. I'm the researcher. I want to support my hypothesis. I want to show that my drug is really working. So I'm taking the evidence as showing that, you see, well, the placebo group took 6.4 days to recover, but the real drug group only took 5.6 days to recover. There's a difference of about 0.8 days. So less than a day. There's a less than a day difference. I think this difference is caused by my medication. It's because my medication works. That's why the experimental group recover faster than the control group. This is my opinion. This is my interpretation of the data. But you have to be critical. Other researchers, other scientists must be critical and must offer counter-argument. How do you offer a counter-argument? You may say, no, wait a minute. Well, there is indeed a difference between the two groups, 5.6 days versus 6.4 days, but this might not be caused by your medication. How do you complete this counter-argument? what's your criticism? What's your counter-argument? What's your alternative explanation for why there's a difference in the days it took the two groups to recover? Your counter-argument may be, no, the difference is not caused by your medication. Your medication has no effect. It's just luck. You are just lucky. You are lucky to get this kind of results. And I may offer a counter-argument. No, it's not because my luck. I did everything right in experimental design. I took random samples from the hospital, 10 of them. They are very representative of the patient population. And also for these 10 people, I randomly assigned 5 of them to receive the real medication, randomly assigned the other 5 to receive the placebo. And you can, if there's any pre-existing differences between the two groups, by random assignment, the differences should be even out. So basically, the two groups should be equal in all relevant aspects before the medication. And if I observe any difference, between the time it took the groups to recover, it must be due to treatment effect. It must be caused by medication, because everything else between the two groups should be equal. This is my argument. But then the critic can offer a counter-argument. Well, even if you randomly assign half of people to receive the real medication and the other half to receive the placebo, there might be still a chance, still a possibility that you are so lucky. You are so lucky that you get a group of patients who are younger, who are less sick, who have a better immune systems in your experimental group. There's still a risk. The risk is above zero. The risk is no zero, that you are lucky enough to have some pre-existing differences between the two groups before the medication. And there's also a possibility of measurement error. So the way you measure recovery, the way you measure temperature, the way you measure symptoms might slightly differ between the two groups. The researcher may make mistakes. The mistakes might be a result of your difference between the two groups, 5.6 versus 6.4. So we can argue and argue. We can argue and argue and never be able to settle the debate. Fortunately, science has established a way to settle the argument. This is how we settle the argument. Let's reach into agreement. Let's set some rules in resolving scientific debate. So, in scientific research, we start with a no effect assumption. We start from the assumption of the critic of the theory. Let's start with your assumption. Let's assume the drug has no effect. The drug just has no effect beyond placebo. It doesn't do anything to people's improvement, to people's immune system, to people's recovery beyond the placebo effect. Let's assume this. This is called the null hypothesis. The null hypothesis assumes there's no difference, no effect between the treatment and the control conditions. The treatment doesn't work. Suppose the treatment doesn't work. What is the possibility that we get this kind of result? 5.6 days for one group versus 6.4 days in the second group. What is the likelihood we will still be able to get this difference by pure luck? or by measurement error, or by some kind of freak chance. If the probability of getting this kind of result, 6.4 versus 5.6, is large, then the critic wins the debate. Okay, well, the risk is too large. The risk of getting